Hey there, and today we'll be looking at quantum computing versus normal computers and how quantum computers can give us a new path to solving many problems. Like for examples, Google's will the Sycamore chip did a problem like a time ago that it took will take 47 years for the world's fastest supercomputer to do, and then Willow did a calculation just a few minutes, which would have taken a classical supercomputer 10 septillion years to complete the calculation. So basically, what do the classical computers do? Like, what is the difference between quantum computers and classical computers? So basically, to understand how a normal computer does calculations, we first need to look at the components, starting from CPU, which is called the central processing unit. The CPU is the brain of the computer and is designed to handle general purpose processing tasks. It can execute a wide range of instructions required to run an operating system, software applications, and user inputs. How it works? Architecture. CPUs typically have a few powerful cores like 8, 4, 16 cores, etc. that focus on sequential tasks. It follows a set of instructions like a times 86-bit ARM that's how to execute code. Control unit and arithmetic logic unit. These two are located in the CPU. So now we're going to look at how these two basically are the main foundations of a CPU. The control unit of a CPU manages the execution of instructions. The arithmetic logic unit handles arithmetic, add, subtract, etc. and logic and or not operations. Cache. Small fast memory inside the CPU to store frequently used instructions. Registers. Temporary. So basically the registers are temporary storage for small pieces of data that the CPUs currently working on. So let's just say, we're using a calculation. We're trying to play games like Roblox or any other game or any other calculations and that stuff. So basically, it's gonna store the small data pieces in the registers temporarily, but will delete them once it stops working on it. How does this perform calculations? The control unit fetches instructions from memories. It decodes the instructions to determine what actions to take. It sends the data to the ALU, which performs arithmetic and logic operations. Results are stored in registers and or are sent back to the main memory. Performance. Single-threaded and multi-threaded tasks. CPUs excel at tasks that require decision-making and sequential execution. It is also suitable for handling operating system instructions and software logic. CPU is determined by clock speed, 3 GHz, 4 GHz, and the number of cores. Bottleneck. When processing thousands of simulated data points, like for AI models, the CPU struggles since it works in fewer tasks. That's why CPUs are not generally used for these AI tasks. The AI models in these computers, like for example, a Samsung phone has Galaxy I or Apple Intelligence. They have something called MPU and they also use a GPU. The AI also uses those too. So now now that we have seen normal computers and its history in action, now we're going to take a look at quantum computing and how its efficiency outnumbers many supercomputers. So basically, what is quantum computing's definition? What does all of this mean? So basically, quantum computing is a revolutionary approach to computation that leverages the principles of quantum mechanics. The three key concepts that differentiate quantum computing from classical computers are superposition, entanglement, and interface. These are really powerful tools that show the distinctive features of quantum computing. So, and quantum computing is just in its baby stages. So basically, let's pretend that let's make an example of the human life cycle. Quantum computing is just in its baby steps. It has yet to evolve to a child and even an adult. But Thanks to companies like Google and IBM, we have developed quantum computers. We have a sense of how it could be. So far, only 100 qubits are way more powerful than Love's classical supercomputers. But still, quantum computers give rise to errors. So basically, Google's real chip is something special. The more qubits you have, the less errors you get. But in reality, it would have been opposite, but Google has found out a way, which is revolutionary. And it has paved hope for companies to find new ways to cool down quantum computers, because you have to make it very cold, make it absolute zero, minus 222 degrees Celsius. It's really cold. And also quantum computers are not something that's going to replace traditional or classical computers, because classical computers are still good at certain tasks. So it's very important that you don't say, oh, quantum computers will be like replacing these traditional computers. No, they will not. Okay, it's just a new way to find new certain calculations to understand them faster and painful for medication, the natural process of the environment, etc. Now that we have seen quantum computing's definition and how the normal computer, classical computers, works, now we're going to dive into what makes quantum computers different. What is so special about quantum computers? What makes it unique in its own sense? So basically, quantum computing leverages quantum mechanics, and it has three key concepts, which are superposition, entanglement, and interface. Now, we're gonna dive into how these three make quantum game changing for math calculations and even solve calculations that we are troublesome. For example, I told you that real example. Oh, 10 septillion years is way too much. It's way too much time to wait for, just for a simple calculation to be done. So now we're gonna see what are these three. So what's the superposition? Superposition is like allows quantum bits or qubits to exist in multiple states at once. So what I mean, let's talk about bits. So in classical computing, a bit can either be 0 or 1. A qubit or a quantum bit, however, can be in a state that is in a combination of both 0 and 1 simultaneously. This makes it game changing, such as both 0 and 1 at the same time, which makes it way more power efficient, makes it way more efficient overall. No need for that many transistors. Already, just 100 qubits is already way more powerful than the best supercomputers in the world. The state of the qubit is represented as the equation shown. Here, A and B are complex numbers representing the probability amplitudes of the qubit being in state 0 or 1. The probability is given by A squared and B squared, and they must add up to 1. They can't just be 2 or 3 or 4. It can't be 0. Both is 1 and 0 at the same time. They must add up to 1. Why does all of this matter? Superposition allows qubits to process multiple possible solutions at the same time. For example, while a classical computer would check one path at a time, a quantum computer can analyze multiple paths simultaneously. This is one reason why quantum computers have the potential to solve certain problems like factoring large numbers much faster than classical computers. But if you read carefully, it says certain problems. Not all problems can be solved by quantum computers. Some areas quantum computers are weak due to the errors I told you. But still, certain problems like this factoring large numbers, it's really game changing what quantum computer can do to the whole world. Now we'll be looking at entanglement and how is it game changing for quantum as well. So basically, what does entanglement in qubits mean, or quantum bits? It's either so this is basically a quantum phenomenon when two bits are entangled. It becomes such correlated, in such a way that one qubit state depends on the state of another, no matter how far apart. So let's explain what this means. When two bits are entangled, measuring the state of one qubit easily determines the state of another, even if it is separated by vast distances. This spooky actually the distance Einstein called it is a purely quantum phenomenon with no classical counterpart. So once we get to the next slide, I'll tell you more about how basically Einstein thought about this. What did Einstein think about this? Because he did not agree with this at all. He thought that this was completely wrong and Planck was wrong. But in the end, Planck was right. Example. Suppose two qubits are entangled in such a way that are in a state 1 by 2 squared, 2 by binary 0 plus 0 1 1. If you measure the first qubit enters 0, the second qubit will also be 0. If you measure the first qubit enters 1, the second qubit will also be 1, no matter how far apart. Just a disclaimer, if two qubits are entangled, the state of the system cannot be described independently. You must describe the joint state of both qubits. You can't just describe one joint state. Why does it matter? Because entanglement allows for quantum parallelism and enables protocols like quantum teleportation and quantum cryptography. It allows 12 qubits in a quantum computer to work together in a way classical bits never could, enabling faster problem solving for optimization problems, cryptography, and more. Interface occurs when probability amplitudes of quantum states add up, which is a constructive interface, or cancel each other, which is a destructive interface, affecting the likelihood of observing certain outcomes. So what does this mean? So they have these things called probability amplitudes, which can be positive or negative, even complex numbers. It can be probability, it can be positive or negative. Just making it clear because it's going to be really important. When quantum states interfere, these amplitudes can combine to reinforce constructive interface or cancel destructive interface each other. During a quantum algorithm, interface is used to amplify the correct solution and suppress the incorrect ones. So one of the reasons quantums can find the needle in a haystack with quotation marks much faster than classical computers. If you think about waves, two waves meeting each other in a phase create a larger wave constructive interface, while two waves phase out each other, cancel each other. Similarly, in quantum computing, the algorithm is designed so that wrong paths cancel each other out, and the paths leading to the correct solutions are amplified. Why does it matter? Because interface is key to how quantum algorithm like Grover's and Shor's algorithm achieves speedups over classical algorithm. By cleverly designing is a key. Quantum computers to interfere with themselves. Quantum computers are able to search unsort ways and factor large and exponentially faster than classical computers. So what's the summary of the key differences? Superpositions. Qubits exist in multiple states at once. Qubits in entanglements are become linked independent and interface probability amplitudes add or cancel. These are the foundation of this, and it's really important to know about these. Now we will look at a brief history. Don't forget to like and subscribe to help support out this channel. So anyways, thanks for watching another video with Unpacking Mysterious Stuff with AZ. Stay tuned for our next video on quantum computing part 2, which will probably come out today or tomorrow. Okay, anyways, thanks for listening to another video. Bye.